Okay, once again, we have another combined mass question where we've got a 5 kilogram mass connected to a 4 kilogram mass, which is then connected to a 3 kilogram mass. There's two ropes that are in this system. Rope 1 creates a tension called T1, which I've labeled in the diagram. I'll talk about those forces in a second. And rope 2 will create a tension T2. So let's look at our free body diagram. The obvious ones are force of gravity. All the masses have a force of gravity directly towards the center of the Earth, or in other words, straight down. So I've labeled the 5 kilogram mass, I've called that mass 1, so there's an FG1 straight down. The 4 kilogram mass I've called mass 2, straight down, FG2. And the 3 kilogram mass 3, is FG3 straight down. Now, as far as the ropes go, ropes can only pull, so it's pulling away from the object at all times. And in any given combined mass system, if the rope connects two masses, if we're not including the pulley or the mass of the rope or anything like that, which we are not, then the tension is the same. T1 equals T2. So the rope 1, we're calling it, simultaneously pulls upwards on the 5 kilogram mass on the left-hand side of this machine, and also upwards on the 4 kilogram mass, slowing it down. So these two tensions, both these T1s, are both pointed upwards in this diagram, and they're equal. T2, same thing. It's pulling downwards on the top mass, the 4 kilogram mass, so down, pulling it downwards, and simultaneously holding up the 3 kilogram mass. So these two T2s are equal and opposite as well. Now that's going to help us. You should be catching on by now that when you look at the entire system, if you've got equal and opposite forces, they cancel. So if I'm going to set up my free body diagram for the entire system and then solve for the entire system, it's very likely that all these T's will not be included. They're going to cancel each other off. So let's come up with our equation of motion. I'll do it in pink. First thing you want to do is estimate or guess, if you can, which way the thing's going to move. Well, if I've got a 5 kilogram mass on this side and a total of 7 kilograms on this side, it's obviously going to start to rotate clockwise. So my acceleration is around the corner like that. There's my acceleration. Now remember the rule when we're setting up our dynamics free body diagram and our equation of motion. Any force that's in the direction of the acceleration is going to be positive. So if we go through and label all this T1 will be positive, it's going with the motion. FG1 is going against it, so it's negative. Then it rounds the corner, so these masses are accelerating downwards now, which means this T1 is actually negative. This FG2 is actually positive. This little T2 right here, pulling down on the 4 kilogram mass, is positive. This T2 below it is going against the motion, so it's negative, and FG3 is positive. So notice I've got, for every T1, I've got an equal and opposite T1, so they cancel. This T2 cancels with this T2, equal and opposite. So what's left? I'm not even going to write the tensions in. When I look at the entire system, when I say my net force is the sum of the forces, what's left over? FG1, FG2, and FG3. We just got to get the signs right. So F net is always MA, and because I'm using the entire system, this is our total mass. FG1, if I start on that side, is negative because it's going against the motion. And then these two FG2s and FG3s are both positive. So now I can go ahead and solve. My total mass, 5 plus 4 plus 3, 12 kilograms is my total mass. I don't know my acceleration. I'm trying to figure that out. FG1 is negative 5 times 9.8. Remember, FG is always mg. FG2, positive 4 times 9.8. FG3, positive 3 times 9.8. And when I work all of this out, work out the right-hand side and divide everything by 12, I get an acceleration of 1.6 meters per second squared. And it does have a direction. It is clockwise. We'll just go CW for clockwise. Counterclockwise would be CCW. So there's my direction. So now we've got the acceleration. Now we want to figure out the tensions. So remember now, if you're trying to find those tensions, you can't use the whole system because it ends up canceling off and the equations are useless. So you have to start isolating individual masses. But you want to be smart about it. You don't want to do a whole bunch of work if you don't have to. So if I go back and I look at my masses involved, let's do this in yellow. I can choose the 5 kilogram mass. Well, how many forces are attached to it? T1 and FG1. So that's a fairly simple equation of motion when I start to use this mass. If I look at the 4 kilogram mass, I've got 3 forces attached to it. T1, T2, and FG2. Notice T1 and T2 are both unknown. So I'd have 2 unknowns in this particular equation if I set up that little isolated mass. But if I look at FG3, again, just 2 forces, FG2 pulling it up, FG3 pulling it down. A much simpler equation. So try and be smart about it. Remember, to get a solution, you only want one unknown. And if you kind of go through mentally here, I don't know T1, I'm looking for that. FG1 I can figure out, it's 5 times 9.8. It's very likely I can solve for T1 using just this mass. So let's look at mass 1 first, which is our 5 kilogram mass. So if I quickly draw my free body diagram, which we already have, there's my 5 kilogram mass, and what's attached to it? I've got T1 up and FG1 down, and we know this whole thing is accelerating upwards on this side. So my net force, which is the sum of forces, will be T1, which is positive because it's going with the acceleration, minus FG1. So if I solve this for T1, T1 is F net plus FG1. Now plug in the values. F net is always MA. FG1 is mass 1 times G. And this mass right here for F net, because the free body diagram that I used to create this equation was just the 5 kilogram mass, this will also be mass 1. So to solve for T1, I simply go 5 times my acceleration, which we've just figured out, 1.6, plus 5 times 9.8, and I crank that through and I get 57 newtons. Now what about T2? Now again, we know T1 now. We figured out it's 57 newtons. So I could use the 4 kilogram mass to solve for T2. That would be my only unknown. But again, there's 3 forces acting on this. It's a little bit more effort than just using the bottom mass, which only has 2 forces acting on it. T2 happens to be one of them. So let's save us some effort and use the bottom one. I'll do it in green. So if I use mass 3, which is our 3 kilogram mass, and construct my free body diagram once again. There's my 3 kilogram mass. Directly attached to it is T2, pulling it up, and FG3, pulling it down. Now for this mass, because it's moving downwards, remember the whole thing's moving clockwise, our acceleration is down, which means FG3 will be positive. So when I write my equation of motion, I get F net equals FG3, that's the positive one because it's going in the direction of the acceleration, minus FT2. F net is MA, so if I solve this for FT2, it will be FG3 minus F net, which is M3G minus MA. And this M, because of the free body diagram that created the equation, was just the 3 kilogram mass, will just be mass 3. So FT2 will simply be 3 times 9.8 minus 3 times 1.6, which ends up giving me 24.6 or 25 newtons.